Today we will start our third lecture of the course Artificial Intelligence. In the last 2 days we talked to the first module, which was an introduction. Today we will start on the second module, and the first lecture is on state space search. Before I continue on to this module, I would like to discuss the questions from the previous module. So let us go back to the questions of lecture 1. The first question was define intelligence. The answer, intelligence, is actually a rather hard to define term. It is often defined in terms of what we understand as intelligence in humans. Alan Newell has defined intelligence as the ability to bring all the knowledge of a system to bear on the solution of a problem. A more practical definition has been given in the context of building artificial systems. Intelligence is the ability to perform better on tasks that humans currently do better. So that was question number 1. Question number 2 of the first lecture was, what are the different approaches in defining AI? And there are 4 approaches: thinking rationally approach, the acting rationally approach, the thinking like a human approach, and the acting like a human approach. The third question was, suppose you design a machine to pass the Turing test. What are the capabilities such a machine must have? The answer is, the machine must be capable of natural language processing in order to understand the questions that the interrogator is posing to it. Secondly, the machine must have capability for knowledge representation to represent not only the prior knowledge about the world, but also the facts given to the machine by the interrogator. Thirdly, the machine should have capability for automated reasoning so that it can do inferences based on the facts that it knows. Finally, the machine must have capabilities of machine learning so that it can learn and adapt to new situations. Also, in order to pass the so-called complete Turing test, or to really act like a human, the machine would also have to have expertise in computer vision as well as robotics. The other 4 questions from the first lecture: design 10 questions to pose to a machine or man taking the Turing test. I leave it to you to design appropriate questions. Same for the next 3 questions. Will building an artificial intelligent computer automatically shed light on the nature of natural intelligence? Well, in a sense, yes, because people who propose the thinking humanly approach to intelligence believe that if we can have a deep understanding of how humans reason, we can build machines like that, and vice versa, we can gain some insights. But I leave it to you to give your answers to the question. Same for the next 2 questions. Now let's go to lecture 2. The first question was, define an agent. The answer is straightforward. An agent is anything that can be viewed as perceiving its environment through sensors and executing actions using actuators. The second question was, what is a rational agent? A rational agent is one who selects an action based on the percept sequence that it has received so far, so as to maximize the expected performance measure given the percepts it has received and the knowledge possessed by it. So, within the bounds of what the agent knows and what are the percepts that it can receive, the agent should behave so as to maximize its expected performance measure. Third question, what is bounded rationality? A rational agent that can use only bounded resources cannot exhibit the optimum behavior. A bounded rational agent does the best possible job of selecting good action given its goal and its bounded resources. So, if the agent has only limited time in its disposal and limited memory or other resources, the agent should do the best that it can under the circumstances. That is the definition of bounded rationality. Fourth question, what is an autonomous agent? So, autonomous agents are those agents that are capable of independent action in environments which are dynamic and unpredictable. An autonomous agent needs to learn and adapt to a new environment. The fifth question, describe the salient features of an agent. An agent perceives its environment using sensors. An agent takes actions using actuators. A rational agent acts so as to reach its goal or to maximize its utility. Reactive agents decide the action on the basis of their current state and their percepts. Deliberative agents reason about their goals to decide their action. Question number 6, I asked you to find out about the Mars rover. So, these are the questions that we want to answer about the rover. A was, what are the percepts of this agent? B, characterize the operating environment. C, what are the actions the agent can take? D, how one can evaluate the performance of the agent? And E, what sort of agent architecture do you think is most suitable for this agent? Now, let us look at the answers to these questions one by one. Firstly, about the percepts that the agent receives, we looked at the website of the agent Spirit. Spirit is one of the Mars rovers that we talked about. Spirit's sensors include panoramic and microscopic cameras, a radio receiver, and various spectrometers for studying rock samples, including an alpha particle X-ray spectrometer, Mossbauer spectrometer, and miniature thermal emission spectrometer. The operating environment of this rover, it's supposed to operate in the Martian surface. This environment is partially observable. This is in fact a very realistic environment. This is a partially observable environment. The environment is non-deterministic. It is sequential, that is not episodic. The environment is dynamic. It is continuous and not discrete. And we can look upon it as a single agent environment. However, if we are modeling other agents or the interaction of this rover with the mothership, then we can look upon this as a multi-agent environment. But otherwise, this can be modeled as a single agent environment. What are the actions that this agent can take? Now, this rover Spirit has the following actuators. It has motor-driven wheels for locomotion. It has a robotic arm with which it can bring sensors close to interesting rocks. It has a rock abrasion tool, or RAT, which is capable of efficiently drilling holes in hard volcanic rocks. Spirit also has a radio transmitter for communication. The final question was, or rather question number D was, how can one evaluate the performance of this agent? Now let's look at the possible performance measures that we can design for this agent. A Mars rover may have the task of maximizing the distance that it has traversed, or the exploration, the diversity of the exploration that it has carried out, or the variety of terrain that it has traversed. Its performance could be measured by seeing how much variety of samples it has been able to collect, or whether it has been successful in finding water or finding life. We already know that the Mars rovers were successful in detecting traces of water in Mars. There could be other criteria such as maximizing the lifetime or minimizing the power consumption, and there are other goals like if it crashes or runs out of power, it cannot explore, so it should. So there are various ways in which we can define the performance of this agent. The final question on the Mars rover was, what sort of agent architecture do you think is most suitable for this agent? In my mind, a hybrid architecture which has components of both stimulus response or reactive type of architecture as well as deliberative architecture would be ideal. For example, I would visualize a model-based reflex agent for low-level navigation and a goal-based or utility-based agent for other tasks like route planning, experimentation, etc. And then the next question was the same questions about an internet shopping agent, and let's look at some of the answers. For the internet book shopping agent, the sensors could be the ability to parse web pages or interface for user requests, getting requests from users, being able to parse web pages. Those could be looked upon as sensors for an internet shopping agent. The environment that it acts in is the internet. This environment is partially observable. It is partly deterministic, sequential. It is static but not quite, because the web is changing. The environment is discrete, and it's usually single agent unless we are trying to model auctions and other such things, in which case we go for a multi-agent environment. The third question was, what are the actuators of this agent? The actuators, that is the actions that this agent can take, is that the agent can follow links, it can fill in forms, it can give information to the user. So these are the actions that the agent can take. D, we wanted to look at the performance measure of the agent. This agent, its performance is whether it has been able to obtain the requested items or books, whether it can minimize cost of the books or time to fetch the books, and so on. And the agent architecture that we visualize is, we have a goal-based agent with utilities for open-ended situations. So it can, situations which are not very well specified, we can have a utility-based agent, but mainly we can have a goal-based agent which has a particular goal in mind, for which it has to minimize the cost and the time. Now we come to our second module. This module is on problem solving using search. The first lecture today, we will introduce the concept of state space search. Instructional objectives for this module. In search, our objective is that the student should be familiar with various search paradigms, which we will deal with these various search paradigms like depth first search, breadth first search, uniform cost search, iterative deepening search in subsequent lectures. In today's lecture, we will look at the basic formulation of search problems as state space search. At the end of today's lecture, the student should understand the state space representation and gain familiarity with some common problems which can be formulated as state space search problems. The second objective is, after the student has taken this course, has learnt this material, he should have this following capability. Given a problem description, he should be able to formulate it in terms of a state space search problem. Should be able to do the state space decomposition of the problem, decide how a state should be represented, how state change takes place, model actions, and formulate the whole problem as a state space search problem. Thirdly, the student should understand how implicit state spaces are described and how implicit state spaces are unfolded during search by making the generated state explicit. Fourthly, the student should understand how states can be represented by some features of a state. Now, before we come to the state space search problem, let us review the definition of an intelligent agent, and let us see how search is important, or why search is important to an intelligent agent. Now, to recapitulate, we have this agent which is working in this environment. The agent receives percepts from the environment which the agent visualizes, and the agent takes actions using its actuators which change the state of the environment. A goal-directed agent, as we have seen, needs to achieve certain goals. Many problems, today we will see that many problems can be represented as a set of states and a set of rules how one state is transformed to another. And in these problems, the agent must choose a sequence of actions in order to achieve its goal. And we will see that such goal-based agents can be modeled using state space search. Each state is an abstract representation of the agent's environment. It is an abstraction that denotes a configuration of the agent. A state denotes the current configuration of an agent. It is an abstract representation of the current configuration of the agent, which is sufficient for solving the problem that the agent needs to solve. The initial state is a description of the starting configuration of the agent. An action or an operator takes an agent from one state to another state. So, and by taking an action, the agent moves from a current state to its successor state. A plan is a sequence of actions that the agent can take. So, a plan is a sequence of action, and the agent starts from the initial state, executes a plan, that is, takes a sequence of actions so that it reaches a goal. A goal is a description of a set of desirable states of the world. Goal states are often specified by a goal test. So, we can say that the following are the possible goal states, or we can say that any state which satisfies the goal test is a goal state. We will take up examples to illustrate this. So, a plan or a path, as we said, is a sequence of actions, and the cost of a path is a positive number, which is usually the sum of the costs of the different steps or the different actions which are part of the path. Now, in this class, we are going to talk about problem formulation. What is problem formulation? Problem formulation means choosing a relevant set of states to consider and a feasible set of operators for moving from one state to another. So, given a problem, we want to formulate the problem in terms of a set of states and a set of operators or actions. Search, as we will see, is the process of imagining sequences of operators applied to the initial state and checking which sequence reaches a goal state. We will elaborate on this further. Now, let us look at what constitutes a search problem. S is the set of states. S is the complete set of states. S0 is the initial state. S0 is member of, small s0 is member of the set of states capital S. Okay. So, suppose this is the representation of a state space and these circles here are the different states. Okay. So, this is the set of states or capital S. S0 is the initial state. Suppose this green circle here, this is the initial state S0. A is the set of actions. A is a mapping from S to S. An action takes the agent from one state to another state. G is the set of final states. These red circles are the goal states in this case. A search problem consists of finding a sequence of actions which transforms the agent from the initial state to a goal state. For example, from this initial state, the agent might have available 3 actions. If he takes action A, he goes to this state. If he takes action B, he reaches this state. If he takes action C, he reaches this state. So, from this, again the agent can take another action, another action, another action, and then the agent can take a sequence of actions to reach a goal state. Okay. So, this is a state. These are the possible actions that are available from this state. The agent can take one of the available actions from a state. The search problem is, given an initial state, find a sequence of actions which transforms the agent to a goal state. So, a search problem, as we saw before, was represented as a directed graph. In this graph, the states are represented as nodes. The states are the nodes and the operators are the edges between the nodes. The operators are the edges between the nodes and the states are the nodes. The searching process is grossly the following. The agent checks the current state and it can execute allowable actions to move to the next state. Suppose this is the current state, and suppose in this, from this state there are 2 possible operators. This is a state A. Operation A takes the agent to the state X and operation B takes the agent to the state Z. So, A and B are the executable operators in state A. Now, the agent is at A, it takes one of the executable operators. Suppose the agent selects the action B and moves to the state Z. The agent checks if this state is a goal state. If it is a goal state, the agent has reached a solution. If it is not a goal state, the new state may become the current state of the agent, and this process is repeated. That is, the agent finds out the possible operations that it can execute in this current state, and it continues this until the goal state is reached. Now, this is an example of a search space. As you can see, this is the initial state, and these three are the goal states. These other circles are the other states in the system. Now, objective of the agent is to start from this initial state and reach one of these goal states. Now, from this state, the agent can take two possible actions to reach either this state or this state. From this state, again the agent can take two possible actions, and then these are the other nodes that the agent can reach, and so on until the agent reaches a goal state. So, this is the sort of process that the agent carries out. From here, the agent has a choice of going either in this direction or this direction. From here, it can go here or here, and so on. From here, it can go here and here. So, the agent can start from the initial state and explore this state space, and its objective is to reach one of the goal states. Now, let us look at another problem. This is a pegs and discs problem, which is a variation of the block problem or this various towers of Hanoi problem. This particular problem, we have 3 pegs and we have 3 discs, red, blue and green. This picture shows the initial configuration of the problem. We have 3 pegs and we have red, blue and green on peg A. The following operators are allowed. One may move the topmost disc on any peg to the topmost position of any other peg. These are the only allowable operations, and our objective is to reach this configuration where the red, blue and green discs are in this position, same position on peg B, and these are the allowable operators. We will see how we can find a solution to this problem. So, this is the starting configuration. Now, what I will do is I will outline a sequence of steps by which we can move from the starting configuration to the goal configuration, and later we will see how we model the different states. The actions that we will take here is move from A to C, that is move the topmost disc of A to C. The next action is move from A to B. Next action is move from A to C. Next action is move from B to A, then move from C to B, then move from A to B, then move from C to B, and finally we have this desired goal configuration. Now, the next problem that we will look at is the well-known 8 queens problem. The problem constitutes the following. We have a chessboard and we have 8 queens. And according to the rules of chess, a queen can attack any other piece which is situated either in the same row or the same column or the diagonal, one of the diagonals. So, these are the positions in which if we have any piece in these positions, they can be attacked by the queen. The 8 queens problem is the following. Place 8 queens on the chessboard such that no queen is attacking any other queen. Now, how can we formulate the state space from this problem? And then we will look at how to solve this problem as a state space search problem. Now, there are different ways in which we can formulate the 8 queens problem. So, before we look at this, let us look at a typical solution of the 8 queens problems. This is a solution, this is a valid solution of the 8 queens problem, and you can verify that none of the queens are attacking each other. This is an example of a non-solution to the 8 queens problem. Why is it not a solution? Because these two queens are attacking each other, and maybe these two queens are attacking each other and so on. So this is not a good solution, not a correct solution to the 8 queens problem. Now let's look at some possible formulations of the 8 queens problem. In the first formulation, we can say that a state is an arrangement of 0 to 8 queens of the board. So a state is any arrangement of less than equal to 8 queens on the board. So a state is specified by the position of the queens which are currently there in the board. An initial state is no queens on the board. The possible successor functions is add a queen in any square. Suppose in this configuration we have 5 queens. In the next configuration we can add any queen to the board so that it does not clash with the same position. That is, from this board we can have 64 minus 5, 59 possible successor states. The goal test is that 8 queens are on the board and none are attacked. So in this formulation, this is the initial state. This state will have 64 successors depending on the placement of the first queen that we introduce. So this is one successor where we have placed the first queen in this square. This is the second successor, this is the third successor, this is the fourth successor, and so on. We have 64 successors. Okay. And each of these states will each will have 63 successors. So if we start from this state, there will be 63 successors. Okay. So that was one possible way of formulating 8 queens as a state space search problem. We can look at other alternative formulations of the 8 queens problem. In the second formulation, a state is any arrangement of 8 queens on the board. So we always have 8 queens. The state is any arrangement of 8 queens. In the initial state, all queens are at column 1. So this is the board. In the initial state, all the queens are at the column 1, and the successor function is change the position of one queen. The goal test is the same, 8 queens are on the board and none are attacked. So this is the initial state. Now the possible operators are, we can take this queen and move it to another column. Okay. So this particular queen we can move to any of these 7 columns, or we can take this queen and move it to one of these 7 columns. So these are the possible successor states. Now this is a intermediate state for this formulation. At this intermediate state also, we can take one of the queens and move it around. Okay. So this is one formulation of the 8 queens problem. A third formulation is, we describe a state by any arrangement of k queens in the first k rows. So at an intermediate point, we would have a current value of k. Suppose k is equal to 3. This means that one queen is placed somewhere in row 1, another queen is placed somewhere in row 2, the third queen is placed somewhere in row 3. So for k equal to 3, this is a possible state of the system. The successor function is add a queen to the k plus 1th row so that none are attacked. That is, the partial solution does not violate any constraints. So, we take the fourth queen and put it in one of the rows such that the queens are not attacked by each other. So, this is, suppose for k equal to 3, this is a possible starting configuration, and this is a possible, these are the, there are two, let us see in this configuration what are the positions in which we can keep the queen. We cannot keep the queen here because it will be attacked. We cannot, by this queen, we cannot keep the queen here. We cannot keep the queen here because it will be attacked by this one. We can keep the queen in this position. We cannot keep the queen here. We cannot keep the queen here because it will be attacked by this queen. We cannot put the queen here because it will be attacked by this queen. We can put the queen here. So, this state has two successor states. So, what we have seen is that given the same problem, there are different ways of abstractly representing the state space of the problem. When we look at the different search algorithms, we will try to see whether a particular formulation is suitable or good for obtaining a solution of the problem in an efficient manner and in a correct manner. Now we come to the concept of implicit state space. The state space may be explicit or it may be implicit. In an explicit state space, we model explicitly all the states of the system, and we model all the operators, possible operations on the system. So, this is an example of an explicit state space where every state is explicitly modeled. However, in this course we were mainly dealing with very huge state spaces, and it may not be possible or easy to model explicitly all the states of the system. Neither is it necessary. It may not be necessary to spell out all the states of the system in order to find a solution. So, we will look at mainly problems where the state space is implicit. That is, we need not explicitly in the beginning keep all the states. Rather, we give a way of representing the states, and we give methods so that given a state and given an operator, we can generate the next state. We give tests for testing whether the agent has reached a goal state. So, our state space will mostly be implicitly represented. And in this implicit state space representation, the agent will know what is the initial state that the agent is in, but he will not initially need to keep all the states that the system has. He will know the initial state, and he knows the operators and the effects of these operators, so that the agent can unfold the state space. So, he knows that if these operations are applied at this state, these are the states that he can reach. Then if he selects the state for expansion, he can obtain the different other states that he can reach from this state. An operator is a function which expands a node, that is, it computes the successors of the node. Given a state, given an operator, the agent will be able to generate the successor node. So, let us take as an example the 8 puzzle problem. So, many of you may be familiar with either the 8 puzzle or its cousin, the 15 puzzle. So, in this 8 puzzle problem, there is a board consisting of 9 squares, and there are 8 blocks, one numbered 1, 2, 3, 4, 5, 6, 7, 8. So, these blocks are in a particular configuration in this board, and one position is empty. Now, this sliding tile puzzle, we can slide these blocks which are adjacent to blank to the blank position. That is, we can slide this tile 4 to this position or slide tile 8 to this position. And the objective of this 8 puzzle problem is to reach the goal state. So, the goal state is another configuration of this system. There could be various different configurations that we decide for the goal state. Given a particular goal state configuration, the objective of the puzzle is to start from the initial state, slide the blocks around so that the agent reaches the goal state. So, what is the state space representation of 8 puzzle? A state is a description of each of the 8 tiles in each location that it can occupy. The operators are: the blank can move left, right, up or down. Goal test: if the current state matches the goal configuration, then we say that the system has reached the goal state. The path cost is the number of steps or the number of times one has to slide a block in order to go from the start state to the goal state. So, the objective of the 8 puzzle problem is to start from the start state and reach the goal state taking the minimum number of steps. So, let us look at how the 8 puzzle, we represent the 8 puzzle and how we can expand the state space of the 8 puzzle. So, this is our initial state. From this initial state, 2 possible actions we can take. We can either move 4 to the right or 8 up, or rather we can say that we can move blank to the left or blank downwards. If you move blank to the left, we come to this configuration. If you move blank downwards, we come to this configuration. Now, from this state again, blank can move left or down. We do not move the blank right, because then we will go back to this state. So, we can get these 2 are the successor states of this state. Similarly, we can expand this state and we can move the blank either to the left or downwards to get either this configuration or this configuration, and so on. We can unfold the state space of 8 puzzle. So, this is an example, a very simple example of an implicit state space, where we describe the operators, the result of applying the operator. The operators are move blank up, down, left or right. There are 4 possible operators, and we also give the preconditions under which an operator can be applied. We can move blank up only if the blank is not already at the topmost row. Similarly, for each of the 4 operators, we can lay down the preconditions and we can give the effect of, describe the effect of these operators, so that we can unfold the state space. As another example, let us take the game tic-tac-toe or noughts and crosses, which many of you are familiar with. This, by the way, is a 2-person game which cannot be modeled as a search for a single agent, but as that of 2 competing agents. So, in a tic-tac-toe, we have a board configuration like this, and in the first instance, the first player plays a cross. Suppose the first player puts a cross at the center location. Okay. So, in the search tree, the different successors will correspond to cross at the central location and not placed at any of the other 8 locations. Okay. So, not can be placed either here or 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 here. So, these are the possible 8 possible places in which the player can place a knot. Suppose a knot was placed in this location. What are the possible successors? Now, in the next move, the cross can be placed at any of the other 7 locations. For example, the cross can be put either here or here and so on, maybe here. Okay. So, this way we can take the tic-tac-toe problem, represent it as a state space, represent each state by the position of the knots and the crosses. We can represent each state, and we can say the operator, the current operator is either cross or not, and depending on whose turn it is to move, whether it is an odd level move or even level move, and the cross on the knot can be placed in a blank location. Okay. Now, in a state space search problem, so the input is a set of states, a set of operators, and maybe costs associated with the operators. There is a distinguished state called the start state, and there is a goal test which tells us whether we have reached a goal state small g, which is one of the goal states. A path is starts from the initial state, and it is a sequence of actions or sequence of states, and the last state is the goal test. And the objective of the search problem is either to find a solution, that is, find a sequence of moves to take the agent from the start state to the goal state, or the objective could be to find the shortest possible such path. Now, let us look at the description of the basic search algorithm. In the next lecture, we will go into more details about the search algorithm. Today, we will look at the basic idea of the search algorithm. So, let L be a list containing the initial state. So, L is called the fringe. L is a list containing the initial state. L will contain, in the intermediate stage, it will contain the set of states that we have generated so far and that we need to expand. Then the search algorithm executes in a loop. If L is empty, that is, if the fringe is empty, return failure. Otherwise, we select the first node from the fringe. So, select is a function which selects a node from L. It may be the node with the minimum cost. If this node happens to be a goal, then we return the node or return the path from the initial state to this node. So, if this node is a goal, then we return the node, that is, return the path from initial state to node. Otherwise, we apply all applicable operators to node to generate all the successors of node, and these successors we merge into L. So, L is L union the successors of node. Now, as we will see, the various search algorithms differ as to how we position the different successors into the fringe, and consequently which node we select for expansion from the nodes in the fringe. Now, we will run the details of the search algorithm in the next class, but today we will talk about the key issues that we will discuss about search. So, in state space search, we start from an initial state and we expand this state to get other possible states. Now, these states that we get go into the current fringe. We select one of the nodes of the current fringe for expansion. So, this node goes out of the fringe and its successors are placed on the fringe. That is, if we look at this search tree, the fringe constitutes those nodes which are at the leaf of the search tree. Okay. So here there are 5 nodes in the fringe. The search strategy will determine which of these 5 nodes I will expand next. Suppose we decide to expand this node, then we generate the successors and place this in the fringe. Now we have to decide which of these 6 nodes we will expand. Now one thing that we will notice is that if we model our search problem like this, the search tree may become unbounded because of loops in the state space representation. Suppose there is an edge, there is an operator which takes you from A to B, B to C and C to A, right. Now if we say that this is A, this is B, this is C, then the successors of C will contain A, and then again under A we will have this entire tree. So in effect, even if the number of states is finite, the search tree may become unbounded if we unfold it like this tree. So a finite state space may become unbounded because of presence of loops, and in some cases we will see the state space can itself be infinite. So when we talk about a search algorithm, we have to handle these issues. Another issue that we will need to handle is whether, depending on the problem, whether the search problem returns a path or whether it returns a node. Okay. For example, in the 8 puzzle problem, the solution to the search problem is a set of operations, whether up, down, up, left, right, left, 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 down. So, sequence of operations which takes us from the initial state to the goal state. However, for problems like the 8 puzzle, we really do not need to spell out the operators. If we just give the goal configuration, the operators are clear, operators are evident. If we say that this is the initial state, this is the goal state, that is sufficient. Given the goal state, we can find the sequence of operators very easily which take us to this goal state. So depending on the problem definition, we will either decide to return a path or a node. Then very important for the design of a search problem is to discuss how march and select are to be done. That is, when we put nodes in the fringe, when we put the successors of the current generated node in the fringe, where should we put the successors? In the beginning, in the end? So how we should put the nodes in the fringe, and also how select is done. Do we select the first node? Do we select the cheapest node? And so on. And to consider these things, we need to consider certain factors. Is the graph weighted or unweighted? If all steps have same cost, we can model the state space as a unweighted graph. But if different operators have different cost, we can associate weights with the edges corresponding to the cost of that operator, and we will deal with weighted graphs. Then we will need to know how much is known about the quality of the intermediate states. Do we have any information or heuristics to guide the search process? So if we know that out of the nodes available in the fringe, so there are 1, 2, 3, 4, 5, 6, 7, 8 nodes available in the fringe, if we know that this node has very high promise and it is likely to take us to a goal solution fast, we might use that knowledge to expand this node before expanding the other nodes. So if we have some information about the quality of these intermediate states, we can have better search strategies so that we can find a solution fast. And also we need to consider whether our objective is to find a minimal cost path or any path as soon as possible. We will, in the next class, will discuss several problem solving strategies. And when we discuss problem solving strategies, we will evaluate each problem solving strategy by the following parameters: whether it is complete, whether it is optimal, and what is the cost associated. So, a strategy is complete if the strategy is guaranteed to find a solution to the search problem if a solution exists. If a solution exists, the strategy must guarantee that one solution will be found. A strategy is optimum if it has the least cost. The search cost associated with a strategy is the time and memory resources required to find a solution. The time and space complexity of the algorithm is a very important thing that we need to keep in mind and that we need to measure. The various search strategies that we will study are blind search, that without heuristics. In those we have depth first search, breadth first search, iterative deepening search, iterative broadening search, etc. We have informed search that make use of heuristic information. We will also study constraint satisfaction problems, and we will also look at adversary search involving two-person games. So, we will come back to breadth first search and depth first search in the next lecture, and I will end this lecture by letting you think of a problem. You have 3 jugs measuring 12 gallons, 8 gallons and 3 gallons, and you have a water faucet or a pipe from which you can get water, and your objective is to measure out exactly 1 gallon of water. In the beginning you have 3 empty jugs, and your objective is to get 1 gallon of water in one of the jugs, any one of the jugs. Now I want you to think how you can formulate this as a state space problem, how you can represent a state, and how you can get a solution to this problem. So think about this problem and you will see that representation is extremely important for search problems. Now we come to the end of this lecture. Before I end, I will give you a few more problems that you must work out before you come to the next lecture. So I will describe a few problems. For each of these problems, you have to represent them as a state space search problem and specify the initial state, the goal test, the successor function, and the cost function. You must choose a formulation. So you must also, of course, give the state space formulation and discuss how a state is represented. So you must choose a formulation that is precise enough to be implemented. First problem, you have to color a planar map using only 4 colors in such a way that no 2 adjacent regions have the same color. Second problem, the traveling salesperson problem. There is a map involving n cities, some of which are connected by roads. The aim is to find the shortest tour that starts from a city, visits all the cities exactly once, and comes back to the starting city. Problem 3, the missionaries and cannibals problem. There are 3 missionaries and 3 cannibals on one side of the river. There is one boat which carries 2 at a time. The missionaries must never be outnumbered by cannibals. Give a plan for all to cross the river. So that is the end of this lecture. So the next class will continue on search strategies. Thank you.